Hello class, and thank you for watching. In topic 2.11, logarithmic functions, you're going to identify key characteristics of logarithmic functions and use limit notations to express the end behaviors. Now, let's begin by first going over what the characteristics of a log functions are. Now, first of all, a log function, like you recall from the previous lesson, is the inverse to an exponential equation. So the log function is going to look again similar to an exponential, but it's going to simply be reflected across the line y equals x. Now, first of all, the general form for a log function is that f of x is equal to a times log base b of x, where again our base is going to be a positive number not equal to 0, and the value of a cannot equal to 0. It could be positive or it could be negative. Now, regardless if the value of a is positive or negative, the domain for this thing is always going to be real numbers that are greater than 0. So only non-negative numbers are allowed to be used again for this value of x, and in order to evaluate again numbers, which makes sense because since this is equivalent to raising b to some power of y to equal to this x value, well, this x value was always going to obviously be positive since this number is always positive every single time. Now we have two situations for a logarithmic function, so we'll start the one on the left where the value of a is going to be greater than 0. So we have a positive value of a. So y equals, let me get a thinner pen, log base b, or y equals log base b, a times log base b of x. If your value of a is greater than 0, any positive number, then the logarithmic function is going to increase in this directional path, regardless of what the value of a, as long as the value of a is greater than 0. Now, since we're crossing the x-axis here, there is no y-intercept. A log function, again, cannot be less than 0, so there's going to be a vertical asymptote that the graph, again, is going to be bounded by with respect to the x-axis. So the y values can never, the x value here can never be a negative number. So the domain of this thing is going to be values that are going to be greater than 0. And there's going to exist a vertical asymptote that the function is always going to be found, in this situation, to the right of. We're always going to cross the x-axis, going back to the x-axis, we're always going to cross the x-axis at the point of 1, 0 when we have this equation in this general form. Of course, when we start doing vertical shifts, adding a value of k on the outside, and doing a horizontal shift, where we're moving things left and right, then of course this point is going to move according to what that value is. Now let's look at a log function where the value of a is negative. So here we have the same format, y is equal to a times log base b of x. So for this example right here, the difference between having a positive value of a and negative value of a is simply the direction that the graph is moving. For a negative value of a, the graph is going to go downwards instead of upwards. However, this graph still has a horizontal asymptote at the y-axis, which is the vertical line x is equal to 0, and we cross the x-axis yet again at the point 1, 0. And again, that makes perfect sense because the only way that x can equal to 1 is if this entire thing is equal to 0, because remember from the previous lesson, log base b of 1 always ends up equaling to 0, since b to the 0 power is the only way. Again, our base has to be raised to a 0 power in order for it to equal to the value of 1. Okay, so this is the difference between having a negative value of a and over here a positive value of a. Now let's talk about increasing and decreasing. Well, because this function is the inverse to an exponential function, which is a one-to-one function, The inverse is also, again, a function itself. So these functions are either going to always increase or they're always going to decrease. Since they never switch direction, they have no relative extrema. So as you see right here, both of these functions are going up and this function is going down. So they're always either going up or they're always going to go down. Let's now discuss concavity. Now, again, because your exponential function is the inverse to this, the same thing is going to happen to this. A logarithmic function is always going to concave up or it's always going to concave downwards. There is no point of inflection at all, since it doesn't change its curvature and it has no point of inflection. And again, if you look at the graphs, you see again through those two examples that I have where a is positive on the left and a is negative on the right. Let's now move on to end behaviors. Now, for a log function in general form, as the input values of x increase without bound, the output values are going to either increase or decrease without bound. So there is no horizontal boundary on this because it's a reflection of the exponential equation where we have a horizontal isotope. The reflection of this is going to end up resulting in a vertical isotope. Every function on its domain as a result has a vertical isotope at x is equal to 0. So as a result, the left end behavior will occur as x is approaching that vertical isotope of 0 from the right side. Now, as soon as we do horizontal shifts, of course, then the horizontal isotope also moves and the domain is going to be affected, as we'll see in examples of this, at that location, along with, of course, the vertical isotope. Now, to discuss and write this idea in using limit notations, let's look at the two graphs that we have up here. So let's split this into two parts, and let's write the limit behavior, the left and right end limit behavior on this function over here for the value of a being positive. So the value of a is going to be positive in this equation for log a times log base b of x. The left-hand behavior, where the vertical isotope is located at, so as x is approaching to 0, that vertical isotope to this function f of x, the left end is going to be approaching negative infinity. Let me zoom out. As you see right here on this left value right there, okay? The left end is going downwards. It's never going to cross again this vertical isotope, but the y values are going to keep on decreasing without bound. Now the right end, which is occurring as x is approaching positive infinity, well, this function increases, so the right end is going towards positive infinity. So again, as you see, neither end is bounded. What is bounded, again, are the x values. The x values are not going to go beyond the vertical isotope. So one end is always going to be approaching wherever that vertical isotope is. And it usually, again, is the left end. The left end should be approaching the vertical isotope. Now, if your value of a is negative for the function, let me zoom in, for f of x equals a times log base b of x, then the opposite is going to occur, simply going to reflect, and on the vertical isotope, the left end will be pointing upwards and the right end of the function would be pointing downwards. Okay, so as you see, depending on the direction that the graph is going, the y values are always going to increase or they're always going to decrease. So they're always going to either positive infinity or to negative infinity, okay, as x gets bigger and bigger. The right end, again, will always go in the opposite direction. Okay, so now let's look at the back and let's look at example 1. Let's write limit statements for the end behavior of the following log functions, and let's also identify what the domain is. So here we have a function y equals a times log base b of x, okay? Well, we know that the value of a has to be greater than 0 because, again, this graph is pointing upwards, all right? So a has to be positive. So the value of a correlates again to the direction that the log function moves in. Now, because the a is multiplying the entire log, this is resulting in a vertical stretch, so it's affecting again the y values. And since the y value on this point right here is 0, this value of a doesn't affect what the x-intercept is. So our x-intercept is going to be 1, 0, okay? All the other y values are going to simply be stretched by a factor of whatever the value of a is. It does not affect the x-intercept. The only thing that could affect the x-intercept is going to be, again, if I do anything to the x values, multiplying the x by some number or adding or subtracting a number to the value of x, as you'll see later on in this section. So since this value of a is positive and the graph is moving upwards, the left end, again, the vertical isotope, well, I forgot to mention that one, the vertical isotope has not shifted since we're not adding or subtracting anything to the x. The vertical isotope doesn't shift and our vertical isotope is still at 0. So as x is approaching 0 from the right side, the y values of this function, as you see right here, are pointing downwards. This end is going down, so that's going to be negative infinity. And since the graph is increasing, as x approaches positive infinity, the y values are increasing without bound, so that means that they're approaching positive infinity. So this is the end behavior. Now, even though it doesn't ask, let's identify what the domain is. So we can identify the key characteristic here. So our domain here is going to be all the positive values of x. So from 0 all the way to positive infinity. Let's move on to the second example. For example B, again, the general form of this graph, a log function is a times log base b of x. Now, you should be able to recognize that this is a log function simply because, again, we have a vertical isotope and it crosses the x-axis, again, and it curves, all right? Log functions do not alternate, like I said. They never go up and down. They always either go up or always go down, and they cross the x-axis. So we have y equals to a times some log base b of some values of x. Now, while we might not know what the value of a and b are, we do know that because of the direction of this graph, the value of a has to be negative, and of course b is going to be a value that's greater than 1 every single time, okay? So here, since the graph is going downwards, like I said, a is going to be a negative. So if we look at the end behaviors, the vertical isotope hasn't shifted. It's still going to be here at the y-axis, which is x is equal to 0. Which means our domain, I'll write our domain first, is from 0 to infinity. Now let's go back and talk about the end behaviors. Well, since our vertical isotope is at 0, that means on the right end, from the right end of 0, as we approach this vertical red line from the right end, from the right side of 0, the y values are pointing upwards. So your y values are approaching positive infinity. And since the graph is decreasing, on the right end, as x approaching positive infinity, your y values are decreasing without bound, so they're approaching negative infinity. So now let's look at the same situation. We want to identify the end behavior, domain, vertical isotope, all that, when we're actually given the equation itself. Now again, the direction of the graph, again, is correlated by this value of a, right? So since this value of a, again, a times log base b of x, since the value of a is 1/2, and that number is a positive number, that means that our logarithmic function should look like this. Our y-intercept is going to be 1, 0, and the vertical isotope, because we're not adding anything to this value of x, is still going to be at x is equal to 0. So since the graph is moving upwards like this, the left end behavior of this function is going to be negative infinity, and the right end of this function is increasing without bounds, so that's going to positive infinity. Since there is no shift to this graph, no horizontal shift, and we're not adding anything to this x, the domain of this function starts at the vertical isotope and goes all the way towards positive infinity. Moving on to the next example, here we have p of x is equal to -6 times ln of x. First of all, recall that ln of x again is just another the natural log, which is just a log where our base is the natural base of e. Okay. The key thing understanding this, in order to identify what the vertical isotope is, what our y-intercept is, and all the other information, is simply focuses on, again, just this part first, that since the value of a is -6, which is a number less than 0, then the graph is decreasing. So it's going to go up here and go downwards. And again, since this value of 6 is multiplying the entire function, okay, that's affecting only the y value. So only the y values are being stretched by -6. So the negative flips it upside down, and the 6 just makes it longer. All these points are just simply moving farther and farther away from the x-axis. Then this normally would move the the y values from the x-axis. And since the x-intercept is at 0, where the y value at the x-intercept is 0, it doesn't affect the x-intercept, and our x-intercept is still going to be at 1, 0. And the vertical isotope, again, this is not affected by that 6, and our vertical isotope is still going to be at x is equal to 0. Remember, the only thing that's going to affect the x-coordinates, even the vertical isotope and this x-intercept, is if I do something again to the x. Either add something to that or multiply something to that. That affects the x's. So let's talk about the limit behavior. So our limit behavior on the left side is going to be our vertical isotope. So as we approach the vertical isotope from the right side, so that's the left end limit behavior, our graph is pointing upwards. And on the right end, as x approaches positive infinity, the graph is going downwards towards negative infinity. And again, since we did no type of horizontal transformation, we did not do anything to the x, the domain of this is still 0 to infinity. Okay, let's talk about now example 2 and identifying if the function is increasing or decreasing and the concavity. So we'll begin with example A. So for this function here, the general form, again, a times log base p of x will decrease if the value of a, again, is a negative number. Well, how can we tell if the value of a is a negative number and tell that this function is decreasing? Well, by looking at it, we could obviously see that this is going downwards from left to right. The formal definition of a function of decrease is that if the x value, if I get one x value that is less than another x value, all right, so we'll call them x sub 1, x sub 2. So let's say this x value right there to the left of another x value, x sub 2. The function is decreasing if the y value of the first x, so this is y1 in other words, f of x1, so y1, if that y value is bigger than the second y value, y2, which is the notation to represent y2, is to say that we have the value of f at the second x, x2, which is exactly what's going on here. Notice that y1 has a higher y value than y2. Obviously, this point up here in blue is higher than this point down there in green, okay? And then instead of using notations of y1 and y2, the definition uses the notation of f of x1 as y1 and f of x2 as y2. So that's the formal definition to state that a function is decreasing. And again, this is going to be true for every x1 and x2. So this function is decreasing. Now, what about concavity? Well, concavity, we just have to look at the graph, and we can see that this graph is concaving upwards. And because these are log functions, the correlation is always going to be the opposite. If the function is decreasing, the only way that a log function decreases is if it concaves upwards, like we have right here. Of course, when we start doing horizontal reflections, then it could change. But we're going to just simply focus on having a function that's decreasing with a negative reflection, and then if it increases, okay? So the graph of f decreases, which as a result for a log function, the rate of change in other words, the concavity is going to increase. Of f increases. Okay. Now let's look at example B. For example B, the formal definition of stating that something is increasing is the opposite of the previous definition, that for every x1 and x2, if x sub 1 is less than x sub 2, and just in other words, if I pick a point on the left on the x-axis and then a point on the right of that value, then the y values at this first x has to be smaller than the y value at this second x. So y1 has to be smaller than y2. y1 has to be lower than y2, which is true. y1 is lower than y2. But instead of using that notation, the notation instead of using the y's is to say f of x1 and f of x2. But again, this is just simply y sub 1 and y sub 2. So this function is in fact again increasing. And this will be true again for any x and y value. So if I pick a different x and a different x2, that's simply to the right, I'll notice again that that y value is going to be lower than the y value over there. Okay, so that's going to be true for everything. So this function again is increasing. Now, if you look at the concavity, because this function is increasing, this log function can only increase, again, as long as we do not do any type of horizontal reflection. And move this over. So as long as we do not do any type of horizontal reflection, the only way that this graph can increase is if the log function is concaving downwards. So while the graph of f increases, the rate of change of f decreases because it's concaving down. So how can we tell this without the actual graph? Well, again, that's by the value of a. Since in this example, a is equal to -4, a number that is less than 0, then that means that the log function has to decrease. And if it's decreasing, then it has to concave upwards. That's the only way that a log function can decrease. Concave upwards. The only way that a log function can concave upwards is if it's decreasing, if this value is as a negative. Of course, if we do a negative value here, then things change, but we're not going to be focusing on that. We're only going to be focusing on whether this is positive or negative. So this graph, the graph of this function f of x equals -4 natural log of x decreases, and the rate of change increases. In other words, concaves up, okay? And the same thing with this example and the last example that we have right here. Since the value of a is 8, a positive number, then that means that the graph of h of x equals 8 times the log base 3 of x increases. And the rate of change decreases. And again, that's the only way that this can occur. For the rate of change to decrease, for it to, in other words, concave down, to have a log function of concave down, this again has to be a positive number, and the graph of the function has to increase. Of course, there's other ways, but we won't get into those here. And that has to deal again with doing horizontal reflections. But we won't worry about, like I said, we won't worry about that. We're only going to be focusing on that there, the vertical reflection. Now, continue to the next page of our notes. We have a little reference guide on the transformations involving log functions and what they look like. A vertical reflection will look like this. We have the log base b of x, and we're adding or subtracting this value of c to the entire thing. So notice that there is a lack of parentheses. If you compare it to the horizontal transformation will add again that value of c inside the parentheses, again specifically to the value of x. So this is a vertical shift. This is a horizontal shift. Now recall, with horizontal transformations, the opposite is going to occur relative to the operation. So adding a value of c is not going to move things to the right or positive direction. It moves it in the opposite direction, to the left side. So this is going to move things to the left by c units. So we know what this graph looks like. Log base b of x, putting plus c inside here, is simply going to shift the entire x values c units to the left, which means that the vertical isotope is also going to be shifted to the location of x equals to negative c. And then, of course, the opposite. If it's minus c, then that just shifts the graph to the right, and the vertical isotope is going to shift to the right to the location of x equals to that value of c. Okay. Now you have your reflections. We talked about a vertical reflection and how that makes the graph concave upwards. The graph decreases but concaves upwards. And then we have a horizontal reflection. Okay, this horizontal reflection flips these graphs across the y-axis, so we'll have a increasing graph that concaves up, and if our graph is increasing, concaving down, reflecting across the y-axis, makes it a decreasing function concaving down. But we're not going to focus on that. Okay, we're going to be focusing on this section on vertical reflections. And then we have our vertical shrinks, which is again the value of a. If a is a number greater than 1, then it's going to cause a vertical stretch. But if the number is less than 1, then that's going to be a vertical shrink. Okay, and of course, if we correlate this and fuse a vertical stretch with a reflection, we'll be doing both things. The negative sign again just simply makes the log function decrease, and by c scale factor. And then we have the horizontal stretch and shrink. That will multiply the x value with that constant c inside the parentheses. This does affect again the domain, and this does actually, well, not the domain, I'm sorry, it does affect the x-intercept. So whatever this value is, the x-intercept is going to be located at the reciprocal of that value. So 1 over c and then 0. We won't be looking at many examples of this, okay, in today's lesson. What we're really going to be focusing on of all these transformations here is going to be the vertical shift, because that's going to affect the domain and the location of the vertical isotope. Okay, so that's the one we're really going to be focusing on right now, and how that affects again the domain of the function. Okay, now let's look at example 3 and let's find the domain of the log function, and of course let's review some of the other characteristics as well. Let's focus on the domain right now first. So let's look at example A. Notice again that we have this plus 2, but because the plus 2 is not being affected to the x, is not being grouped with parentheses, that means that this is going to be a vertical shift, and this is going to shift the graph of y equals 2 times log base 3 of x 2 units up. So this f of x is going to move this equation 2 units up. That's what the plus 2 is going to do. So it does not affect the location of the vertical isotope. So just to get an idea, look, so let me draw an x and y value right here. And let's do this graph right here, y equals 2 times log base 3 of x in blue. So this graph is going to look, not the blue highlighter, the blue marker. This graph is going to look like this. This blue graph is the equation y equals, again, 2 times log base 3 of x, where our vertical isotope is at 1, our vertical isotope is at x is equal to 0, and the y-intercept is at 1, 0. This plus 2 is going to shift this graph and all of its points 2 units higher. So up 2, up 2, up 2, and up 2. Okay, so this point would be now at 1, 2, at 1, 2, whatever this point is, it will be up 2 units higher, and whatever this point is, it will be up 2 units higher. Now, of course, the vertical isotope is also going to move up 2. But since the vertical isotope is a vertical line, moving this graph up 2 is still going to keep it in the same position of x equals 2. So that vertical isotope does not get affected because this plus 2 is only affecting, again, the y values and not the x coordinates. And the same thing with this 2 right there. This 2, like I discussed in the previous examples, is a vertical dilation. So yet again, it's affecting the y coordinates and not the x coordinates. So the x values, x is equal to 2, and this x equals 1 at this point are not going to change. Well, the y-intercept does change. Let me take that back, because it's going to be moving up 2, so it's not going to be located at 1, 0. It's going to be located somewhere else, whatever unit, again, moves this up to cross the y-axis at that value. I'm sorry, the x-axis at that value. But going back to domain, the domain, in other words, doesn't change. So here, the domain is still going to go from 0 to infinity, because we did not shift the vertical isotope. Our vertical isotope is still at x is equal to 0. The y-intercept is not the same because of the vertical shift, and that messed things up. But the end behaviors is still the same. Because the value of 2, this 2 is positive, the end that's approaching the vertical isotope, which is the left end, is still decreasing without bound. And the right end of this function is increasing without bound. So that doesn't change either, because the plus 2 does not affect, again, the x coordinates. Now let's look at example B. So for example B, we now are affecting the x coordinates because we have a horizontal shift of -3, which means that the graph is going to move 3 units to the right. So if y is equal to -5 times ln of x, okay, if this graph looks like this, and it's downwards because the value of a is negative, where my vertical isotope is at x is equal to 0, and my y-intercept is at 1, 0, because I am now doing a horizontal shift in the right direction, these points are all going now to move to the right, along with the vertical isotope. So the vertical isotope is going to shift 3 units to the right. Let me get it in purple. So 3 units to the right, and this point is also going to move 3 units to the right. So the vertical isotope will now be at x equals 3, and this point, 1 plus 3 is equal to 4, is going to cross the x-axis at 4, 0. Okay, So that would be our y-intercept. I'm sorry, x-intercept. So the domain of this thing, because of this vertical shift, well, let me first write the vertical isotope. The vertical isotope is at x equals to positive 3, and the domain is now going to start at the vertical isotope in 3 and go to positive infinity. Now the end behaviors have not changed from this example here. Since this is decreasing, the left end is still pointing upwards and the right end is still pointing downwards, as you see right there. But what's changing again, at least in terms of the left end behavior, is that x is not approaching 0 anymore. Since the vertical isotope is 3, x is approaching positive 3 from the right side. So that again is what's changing. The x coordinates are affected, so the vertical isotope is affected on the left end, and on the right end nothing changes in terms of notation. Okay, this is still going to be approaching positive infinity, and where a function is that log function that's decreasing, the right end is decreasing, so it's going unbounded to negative infinity. Okay, this is a little bit challenging problem, a little more trickier, because we are multiplying the 2x and the plus 3. This is not an actual shift of 3 units because of the factorization, or I'm sorry, the distribution of the 2 into this expression right here. Remember, the 8 does not affect, again, the domain. What's going to affect the domain is going to be this vertical translation, this horizontal translation, this horizontal shift. So to figure out what that horizontal shift is, since the 2 has been distributed into the expression, we are going to factor out 2 from the inside. So we have 2, and we're going to factor out the 2. In other words, divide both of these things by 2, which is going to be x plus 3 over 2. So this is, in fact, what the horizontal shift is. Plus 3 is going to actually shift things to the left, and that means that the vertical isotope is now going to be at x equals negative 3 over 2. So imagine again your x and y axis. We have a vertical isotope at x equals to negative 3 over 2. Since the value of a is positive, that means that the graph is going to increase, and the graph is going to go like that. Our x-intercept has been shifted from 1, 0 down negative 3 over 2, which when we do the subtraction, 1 minus 3 over 2, that is equal to a value of negative 1.5. So I'm sorry, negative half. Negative 1 over 2. So that's where our our x-intercept is located at. Now, how does this correlate to domain? Well, the domain of this function, since the vertical isotope is at 3 over 2, then that means that our domain is going to start at negative 3 over 2 and go towards infinity. And the end behaviors are the following. Well, the right end behavior is going to be positive infinity. As x approaches positive infinity, your y values are unbounded, increasing and unbounded. Again, since this value a is 8, a number greater than 0, the right end is going to increase, and while the left end again is pointing downwards. So f of x is, the y values are going towards negative infinity. What is going to change is that since we are doing a horizontal shift 3 over 2 units to the left, then this behavior, the left end, is going to approach the vertical isotope of negative 3 over 2 from the right side. So that does in fact change. We have to change this number to that instead of 0. And now let's finally look at this example right here. This is also a little tricky one. We have k of x equals negative 9 times the log base 4. This right here is negative x plus 4. So let's write it like that first. And we're going to use the same strategy as the previous example. A negative sign has been distributed into this entire expression in the parentheses. So we're going to factor out the negative side still inside the parentheses, but factor the negative sign from these two terms there. So we have negative 9 times the log base 4 of negative x minus 4. Okay. Well, the minus 4 is going to shift the graph again 4 units to the right. So that would mean that the vertical isotope is going to be right here at x equals 4. And since this number right here is negative, the graph would normally again look like this. It would be decreasing on the right side of this vertical isotope. But we also have a horizontal reflection, because we're multiplying the inside value with a negative sign, with a negative 1. So that's going to flip this graph from the right side of the vertical isotope to the left side of the vertical isotope. So this is again the example that I was talking about, okay? And while you might not have to do a lot of these again in terms of your homework, but I just want to give you an example of what that would look like, okay? So the graph would look like this. And because we have a horizontal reflection, the domain is going to end with the vertical isotope. So our vertical isotope is at x equals positive 4, because we're shifting it 4 units to the right since this is minus. So our vertical isotope is at x equals negative 4. And because of this negative sign, we're now on the left side of that vertical isotope. So that's going to make the domain go from negative infinity to the vertical isotope. Now, as a result, that changes the end behaviors, and the right end is going to be the end that's approaching the isotope of 4. But since we're on the left side, we're approaching the vertical isotope on the right side from the left. So the right end behavior, I misspoke. So the right end behavior as x is approaching the vertical isotope is now from the left side of that value. So we're going to put a negative sign right there. And f of x, as we see the graph, is pointing upwards. And the left end behavior, which is now negative infinity instead of positive infinity, there's no vertical isotope to the left. So we're going to go all the way to negative infinity. The y values are decreasing without bounds, so negative infinity right there. Okay, so this would be the domain of our function, and of course our vertical isotope. Now, since we talked about the characteristics of a log function, and from the previous sections, characteristics of exponential functions, now let's determine how can we tell the difference if we're given tables of values of a log between a log function and an exponential function. Well, in an exponential function, remember that the format, the general form, I'll write it up here, the general form for a exponential function is that f of x is equal to some value of a times a base to the power of x. So the x values, again, are going to be the input values. So over an equal length input value, your y values are going to be proportional. So if my x values are increasing again by equal lengths, hopefully by 1, then the y values are going to be growing again in a proportional rate, in a geometric sequence, meaning that you're going to have a common ratio. Like this example right here in letter B. Notice that all my x values are increasing by 1, but all my y values are increasing by 3. So this is going to be an example of an exponential function where my common ratio, b, is 3, since that's what I'm multiplying to get to the next value. If I want to figure out what the value of a is, well, that's easy. Remember, for these examples, the value of a is our y-intercept. So since our y-intercept is 0, 1, that means that the value of a equals to 1. So this is exponential. Now a log function simply gets me the reciprocal of this. Since the inverse to an exponential function is a log, log base b of x would be the inverse to this. Well, of course, times a, of course, also a, right? The inverse to this is this part right there, log base b of x. So that would mean that the x and y values are going to flip. So over an equal output values, the x values are going to be proportional. So if the input values of an additive transformation function on any function f are proportional, so if these x values, input values, are proportional over equal length output values, so these values are increasing by units of 1 or an equal length value, then this is going to be an example of an exponential function. So for example, notice that this time the y values are the ones that are increasing by 1, and the x values are increasing by a factor of 4. One times 4, 4 times 4, 16 times 4, and 64 times 4 gives me those values. So this is an example of a log function. And we know what the value of b is. The value of b is going to be 4. This one, it's kind of hard to figure out what the value of a is. Since the values of a, the y values are increasing, we do know that the value of a will be positive, but it's going to be hard to determine what that actual value of a is because of the scale factor. But we do know that the value of b would be 4. So the function will look something like this. So that number would have to be 2 if I use inverse operations. 2, 6, or if I need to think about it backwards, 6 divided by 3 has to start off with 2. So here the value of k is 2. to the 10th. So that means we're multiplying by so that means that the same thing is going to have to occur right here. To get from e to the first to this next one, we have to multiply another e to the third power, which would be e to the fourth. So that's a good one. So we'll e 7 to an e to the 10th. We have to multiply the same base of e and increase the 7 by 3 to get to 10. Thank you. Through email or through parents. Have a wonderful day and goodbye.